Download this code from codegive.com, link in the description below. OK, let's break down the concept of RMI, remote method invocation, within the context of distributed systems, drawing from the structure you might find in a lecture like LEC 23 by Bhanu Priya. We'll cover the architecture, key components, the flow of execution, considerations, and provide a code example. Lecture 23, Remote Method Invocation, RMI, in Distributed Systems. Introduction. In distributed systems, we often have processes/objects residing on different machines that need to communicate and interact. RMI provides a mechanism for one object, the client, to invoke methods on another object, the server, that resides on a different Java virtual machine, JVM, potentially running on a different physical machine. It's like making a local method call, but the actual code execution happens remotely. Key goals of RMI. Transparency. Make remote method calls appear as similar as possible to local method calls. The client code shouldn't have to deal with low-level networking details. Abstraction. Hide the complexities of inter-process communication, allowing developers to focus on the business logic of the application. Platform independence. Java-specific, leverage the right once, run anywhere nature of Java to enable distributed Java applications to work across different operating systems and hardware. Simplicity. Provide a relatively straightforward API for creating and using remote objects. RMI architecture. The RMI architecture consists of several key components that work together to enable remote method invocation. 1. Remote interface. This is a Java interface that defines the methods that can be invoked remotely by clients. The interface must extend java.rmi.remote. Each method in the interface must declare that it can throw java.rmi.remote exception. 2. Remote implementation, server. This is a Java class that implements the remote interface. It contains the actual implementation of the remote methods. The remote implementation object must be able to be accessed remotely. This usually involves extending java.rmi.server.unicast remote object, or other suitable base class, and registering it with the RMI registry. 3. Client. The client is the Java program that wants to invoke methods on the remote object. The client looks up the remote object, typically through the RMI registry, obtains a stub, see below, and then invokes methods on the stub as if it were a local object. 4. Stub, client-side proxy. The stub acts as a proxy for the remote object on the client side. It implements the same remote interface as the remote object. When the client invokes a method on the stub marshals, serializes, the method arguments, sends the request to the remote object, and then unmarshals, deserializes, the result received from the remote object before returning it to the client. 5. Skeleton, server-side proxy. The skeleton receives the marshaled method invocation from the client's stub. It unmarshals the arguments, invokes the corresponding method on the actual remote object implementation, and then marshals the result before sending it back to the client's stub. Note: skeletons are mostly deprecated in modern RMI implementations, Java 5 and later. Dynamic proxies are often used instead. However, understanding the concept of a skeleton is important for grasping the underlying mechanism. 6. RMI registry. The RMI registry is a naming service that allows clients to locate remote objects. The server registers its remote objects with the registry, associating them with a name, or URL. The client can then look up the remote object by its name in the registry and obtain a reference to its stub. The RMI registry is a separate process that needs to be running before the server starts. 7. Transport layer * The transport layer handles the actual communication between the client and the server. It is responsible for establishing and maintaining connections, sending and receiving data, and handling network-related errors. RMI uses TCP/IP as the underlying transport protocol. RMI workflow, how a remote method call works. 1. Server registration * The server creates an instance of the remote object implementation and registers it with the RMI registry, associating it with a specific name, example my remote service. 2. Client lookup * The client contacts the RMI registry and requests the remote object by its name. 3. Stub download * The RMI registry returns the stub, proxy, for the remote object to the client. 4. Method invocation * The client invokes a method on the stub as if it were a local object. 5. Marshalling * The stub marshals, serializes, the method arguments into a stream of bytes. 6. Transmission * The stub sends the marshaled request to the server, where the remote object resides, over the network. 7. Unmarshalling, skeleton/server The skeleton, or dynamic proxy, on the server side receives the marshaled request and unmarshals the arguments. 8. Method invocation, server The skeleton invokes the corresponding method on the actual remote object implementation. 9. Marshalling, server The remote object executes the method and returns a result. The skeleton marshals the result. 10. Transmission * The skeleton sends the marshaled result back to the client's stub. 11. Unmarshalling, the client's stub receives the marshaled result and unmarshals it. 12. Return * The stub returns the unmarshaled result to the client. Code example. Let's create a simple example, a remote service that returns the current date. 1. Remote interface, remote-date.java. 2. Remote implementation, remote-date-impl.java. 3. Server, dateserver.java. 4. Client, dateclient.java. Steps to run the example. 1. Compile * compile all the Java files using javac remote-date.java remote-date-impl.java dateserver.java dateclient.java. 2. Start the RMI registry * open a terminal and start the RMI registry using the command remirregistry. You might need to specify the class path if the remirregistry executable isn't in your system's path. The path is usually inside the JDK installation directory under bin. E.g., C /program files /java /jdk 1.8.0_291 /bin /remirregistry. 3. Start the server * open another terminal and run the server using the command java dateserver. You need to ensure that the class path includes the directory containing the compiled classes. Example, java.rmi.server.hostname equals 127.0.0.1 cp. Date server. 4. Start the client * open a third terminal and run the client using the command java date client. Again, ensure the class path is set correctly. Example, java cp. Date client. Important considerations and potential problems. Security RMI can be vulnerable to security attacks, especially if you are transmitting sensitive data. Consider using SSL/TLS for secure communication. Also, RMI can download classes over the network, which introduces security risks. Use the java.rmi.server.codebase property with caution, and consider using digitally signed jar files for downloaded classes. Firewalls Firewalls can block RMI traffic if the ports used by RMI are not open. RMI can use dynamic ports for communication, making it difficult to configure firewalls. You can configure RMI to use specific ports. Class loading RMI can dynamically load classes from the server to the client. This can be useful, but it can also introduce compatibility issues if the client and server are using different versions of the same classes. It's often better to ensure both sides have the required classes. Serialization RMI relies on serialization to transmit data between the client and the server. Ensure that all objects that are passed as arguments or returned as results are serializable. Implement the java.io serializable interface. Pay attention to versioning when serializing/deserializing objects over time, as changes to classes can break compatibility. Performance RMI can be slower than local method calls due to the overhead of marshalling, network communication, and unmarshalling. Consider using caching or other optimization techniques to improve performance. Error handling remote method calls can fail due to network errors, server crashes, or other issues. Be sure to handle remote exception properly and provide informative error messages to the user. Distributed garbage collection, DGC RMI uses DGC to track remote object references and garbage collect remote objects that are no longer being used. Alternatives to RMI While RMI has been around for a long time, there are other technologies that provide similar functionality, such as Web Services, SOAP, REST offer broader interoperability across different platforms and languages. Message queues, example Apache Kafka, RabbitMQ for asynchronous communication. gRPC a modern, high-performance RPC framework. Enhancements and advanced topics, relevant to Lecture 23. Object activation allows remote objects to be activated only when they are needed, saving resources. This is useful for objects that are not frequently used. Distributed transactions RMI can be used in conjunction with transaction managers to implement distributed transactions, ensuring data consistency across multiple systems. Security managers RMI can be used with Java security managers to restrict the capabilities of downloaded code, reducing the risk of security vulnerabilities. Dynamic proxies modern RMI implementations often use dynamic proxies instead of traditional skeletons. Dynamic proxies allow you to create proxy objects at runtime without having to explicitly generate skeleton classes. Load balancing you can use load balancing techniques to distribute RMI requests across multiple servers, improving performance and availability. In summary, RMI is a powerful mechanism for building distributed Java applications. By understanding the architecture, the workflow, and the potential pitfalls, you can use RMI effectively to create scalable and reliable distributed systems. Remember to consider security, error handling, and performance optimization to ensure that your RMI applications are robust and efficient. The code example provides a basic foundation that you can build upon to create more complex and sophisticated distributed applications.